we're doing data structures and we're starting the lab 5 stacks. Now, in this lab, we're supposed to be studying all about stacks. There's the next data structure after linked list. I'll show you the questions. Now you should be able to see the question asked. We'll just have a quick go through, a quick rundown of the questions here. If you guys have any other doubts, you can just reach out to me, or you can ask your doubts in the next physical class as well. For the first one, create a generic stack called myStack class using array list. The myStack generic class should implement the following methods. Okay, perfect. Now, what is a stack? A stack is something like this. It's last in, first out. Last in, first out means whatever goes in, the last comes out first. So you add things like this. That's called push. So you push things in, and then you pop things out. So the last thing which went in would come out first. Now, peek is the same as pop, except you don't remove the item, you just see it. Pop removes the item from the stack. Now, get size just tells you the size is empty. It tells you if it's empty. To string converts the whole thing into a string, and search is to search the stack. Now, write a test program. Okay, first let's implement this. There are 5 questions in today's class, today's lab session, and we'll try to just go through it quickly. We'll try to keep the recording short. Now you should see the compiler on the screen. Now in this compiler, let's just try to run it. This is the code for the first question. Okay. The first question was to implement a stack. And as you can see, 1 second. Hold on. Let's change up the names. Hmm. Okay, perfect, it runs. Okay, now what requirements are there? You needed to get a constructor. You have the constructor array list with the array list. You can push out items, you're just adding it to the array list, okay? The only thing you need to realize here is that it should be LIFO, L-I-F-O. So you can implement it using array list or anything you want. All that has to be done is the last item which goes in should come out always. That's it. That's also the difference between the stack and the queue. The queue is first and first out. Now add item, okay? Pop is to remove from the last position. That's it. Remove from the last position of the list always, not from the first one. If you remove from the first, that would become a queue. Now peek is you don't remove it. You just get it or you return the value except you don't remove it. Now get size, fine. Is empty, fine. ToString, fine. And contains, fine. It's easy. Let's go to the next question. Now, write a test program for Q1 called test my stack class. Create a stack of type character from my stack. Okay. So you're trying to create a stack of the type character, then you try to add some stuff. Then in the same test program, as Q and B, create a second type of stack called integer. Fine. Write a new test program called test int my stack class for Q1A. Prompt user to enter integer value. Okay, fine. So we'll finish question one first. Let's look at the B and C part. Now, you should see the next part. Let me show it to you. So let's get the tester class here. Let's make a new file. Okay. Well, let's run it. Okay, so you have everything being done. Let's look at the code. Now, you make a new stack, uh, new my stack called stack. Okay, then you add, it's a type character, fine. For character A up to B, up to C, you add the items. So A, B, C, that's a for loop. Now, system print, you print it out. Fine, fine, fine. Now, search is basically the dot contains. So if it contains this item, then it's there. Now, my stack, integer, stack two, new my stack. Okay, that's fine. This is for integer class. Quite simple. You push the items and then you search. You should solve some questions on this and practice problems for lead code to actually get a hang of this chapter. Now, this one. Create a new test program for Q1A. Prompt user to enter an integer value. Fine, you're just taking input now. That's not really something quite different. You're just taking an input. Let's look at question number 2. Okay. Let's look at the code again. So what are you doing? You're just making an integer stack. And with that, you're going to be adding items by taking the input from the user. Now, the user can just give it using the system input. Uh, the stuff is quite simple here. If you see the size of the stack, done is empty. So it's just a tester class, except now you're giving input. Now for the input, you can just use a scanner. It's fine. Let's look at the next question. Oh, well, there's a bit more to this. Now this may look easy for me because I've been doing this for some time, but if you find difficulty, if you're not able to understand, I would recommend you either reach out to me or you uh, message me, but or you reach out to me or you go to YouTube or Lead Code, you get the book. If you need the book to revise, you can ask me for some good books as well. Now moving on. You write a new test program for question 1A called test int my stack class. Prompt user to enter the integer value. Fine, done. Now push values 1 through the user entered. Push the values 1 through the user entered value onto the stack. Print the size of the stack, display the content repeatedly calling pop until the stack is empty. What is the output of the Y? This is basically last in, first out. It's going to be the opposite of how the user entered. So the integer that the user entered, you add the values from 1 to that value. Okay. Let's try to run this quickly. Okay, we'll go back to the question we're looking at. Okay, yeah, let's resume again. Question 2. We just had to make a test integer class using the stack which we just built and take user input. Now we have our stack here. Let's just compile it. There was some issue with the directory. So just make sure when you're trying to compile the files, you have the correct package names and you're in the correct directory of the folder as well. Now let's say 5, and you get it in the descending order 5, 4, 3, 2, 1. Now this could be used for sorting because if you realize, if you add items based on their size into a stack and then you pop it all out, that would give you some sort of sorted list of numbers. Assuming that an unknown number positive integers are stored in a stack, S, using only stack ADT operations, write an algorithm function to find the sum of every element in S. Okay. So stack after data type operations to find the sum of every element in S. So you want to add all the items in a stack. That's fine. That's okay. We can do that. Let's do that now. T3. Okay, let's run it. Okay, it works. Now, let's see the code and why it works, basically. Let's be a bit more hands-on. So you get a stack, that's fine. You know how to make a stack. So you can just use the built-in stack data type, random. You're adding numbers to it, fine. Now to get the sum, how do you get the sum? While the stack is not empty, you just keep popping it out and then you add everything. So what that means is the sum is 0 in the beginning, and you keep repeating stack dot pop and keep adding that to this variable called sum. This will happen until the stack is empty. So let's say the stack has 3, 4, 5 in it. So you would pop this out, and the sum initially it was 0, but then it would become 5. Add. Now pop this out plus 4. That would become 9. Pop this out, and that would become plus 3. That would become 11. Now, this is your answer, 11. So started with 0, 5, 4, and you keep adding the values to it, which gives you the final result of 11. And if in this case, that is, but over here they're adding 10 digits, obviously the sum is going to be much larger. Now, question number 3. Question number 4. We're done with 3. A string is a palindrome if it spells the same way forward and backwards. Write a Java program to that uses a stack to determine if a string is a palindrome or not. Let your string be of maximum size 15 characters. Note, however, that the actual size may be 15 or less. Max is 15. Okay. Question 5, the Tower of Hanoi is mathematical game or puzzle. Okay, so Tower of Hanoi is a classic problem. I will try both of these. Let's start with question number 4. Let's compile it and now run it. Oh, hmm. Oh, yeah, okay. I think we didn't write the package again. Okay, ABBA is a palindromic string. ABA is also a palindromic string. Hello is a palindromic string, and all of these are palindromic strings. Fine. How do we do it? The way you do this is, let's see, from here. So you have your stack, okay, and you go to the mid. Put the first half of string into the stack, okay, and put the first half into the stack, and then you compare by popping off after the middle. What does that mean? Let's say you have A, B, A. Let's say something else, A, B, B, A. I'm going to put the first half into the stack. That would mean putting A and then B. Now, you don't have these. But then when you take things out, it would give you B first and then A after that. And as you can see, B, A, B, A are the same. And that's how you know it's a palindrome. So you find the mid. Once you find the mid, then put the first half into the stack and then compare with the rest of the half by popping it out, because when you pop it out, it would actually reverse, right? And that's what a palindrome is. It reverses in the middle. So it's a very smart way of basically reversing the initial half and comparing if the first half was reversed, does it match the second half? If it does that, that means it is a palindrome. That's the definition of a palindrome, right? They're symmetrical. So that's about it. You start from here, you push everything in, and then you pop and you compare. If they don't match, then you say false. Otherwise, you say true. This is the code. Okay. Now, this is a classic question, which you always get. Now, question 5, the Tower of Hanoi is a mathematical game or puzzle. It consists of 3 rods and a number of discs of different sizes, which can slide onto any rod. The puzzle The puzzle starts with discs in a neat stack in ascending order of size on one rod. The smallest at the top, thus making a conical shape. The objective of the puzzle is to move the entire stack to another rod, obeying the following rules. Only one disc may be moved at a time. Each move consists of taking the upper disc from one of the rods and sliding it onto another rod, on top of the other discs that may already be present on that rod. No disc may be placed on top of a smaller disc. So what you're doing is basically you have three rods at different sizes. Okay, three, let's say, yeah, three rods, and you have discs of different sizes. You want to basically sort it out into an ascending order of size into one rod. Pretty nice. So you have three rods, and obviously, as you can see, they're closed. One side is closed, and if one side is closed, that's a stack. Q has both sides open. Stack is one side closed. Now, moving on from this, if you can see, so what we're trying to do is we're trying to have the discs arranged in ascending order. So you might have this, but we don't want that to be there. And we want to arrange everything into a neat, convenient order like this. Okay? So this to this and this, like this. So to do that, you would have to do a lot of stack operations because while you're dealing with stacks here, there are three stacks. It's basically a puzzle of how you move things around so that at the end it gets sorted into ascending order. So sorting is a part of majority of our daily life problems, you know. There's a lot of things we can do if we can learn sorting at an advanced level or even the basic level. Now, there are many types of sorting. You should know all the different types of sorting. Just to revise it, I'll give you the names. The names are insertion sort, merge sort, quick sort, binary. Well, that's binary search. Then you have bubble sort. Make sure you know all of these different algorithms. Now, algorithms is a different course, but you need to revise some basic stuff, obviously. Sorting is quite basic. Now, let's get to it. Okay, we need four files for this. We need recursion. The different methods actually you can have, you can do it iteratively or you can do it by recursion. Let's first make our integer stack. So Java util iterator stack. Okay, we have this. Now the only thing is this one, stack.iterator. Now what does that do? What is this stack.iterator? So the iterator is an object that can loop through a collection, such as an array list. It basically allows you to remove elements from the collection. So it's basically able to sequentially traverse any type of array list and stuff. Now, array list stack, all of that can be traversed using an iterator in Java. So it can iterate through any collection basically. You get some cool features like has next, remove, which all collections have. Now, what that does is actually it allows you to iterate through the items in the stack in a well-defined sequential manner, just like how you have a scanner. You say has next int and all that, right? It's similar to that. Now we'll see how we can use it. You should know what these individual parts mean. The rest are the same except this guy. Now moving here. Now let's get the tower for Noe ready as well. Okay. Now we're defining a few things. Basically the rules of the puzzle or the game. So if you start from here, you just want to basically build a tower. Now the disk space. Okay. You retain the string by formatting it. Now this over here is just a bitwise shift operation. Shifting to the left by 1 actually means multiplying by 2. So this is nothing but multiply by 2. And then you subtract 1. So you multiply by 2 and subtract 1. Now we have the rod. The space is the number of disk minus 1. Okay, fine. Tower image. Now you'll have the number of disks and the stacks on the tower. We have iterator, string builder. Okay. So we're just trying to print out the tower. So we're using the iterator has next is just sequentially passing through the stack. Let's try to run it, and then it would make more sense. Compile all the files. Okay, there's an issue. Let's try it again. Okay, okay, compilation done. Again, make sure you have the correct package names. The commands are also correct. Java C for compile, Java for running. Now you may just use your NetBeans or something as well. That's our Visual Studio Code. That's fine. Now let's run tower. Okay. We have 5 disks, A, B, C. You can see it running. Now, what are we doing actually? Look at the method above. Look at the method. The method is quite simple. So you want the third item, right? So you'll put all the other items into one. Let's say you have something here. Let's try to run it again and see how it works. This time, let's run the recursion method. Let's say there's 5. Now, understand, you want to get this back, right? This one. So what you're doing is You will take this guy, put it here. Now you're supposed to take the smallest one. Yeah, this one. Now you want this guy. So all of this will go there. You take this here. And this. And the logic here is quite simple. You want to recreate this, right? Fine. So you move the pieces in such a way that you would be able to get the biggest one on the route of your choosing. Let's say we've chosen C in this case. So you need to remove all the 4 disks and you can't mess it up. You need to make sure the other ones are also removed in a way that's symmetric, sorted in the correct order. So you would take this out in one place, the other one in the other place, and then you return this back. So you are basically building the tower again. And then you take it here, take this here, take something else there, take that there, and then finally this one. Now you take this guy here, this would go there, this would go here, this would now go on top of that, and finally this would go, or in this case, this would go here. And now what you would see is the last one going here, and then back. Now, to give you a better explanation of this, something more interesting, let me perhaps show you a diagram. Okay, the goal here is
Hello everyone. Welcome to Kulpilon's YouTube channel. Today we will be
I think you can watch the YouTube video on your own, but I would like to show you something. This one.
I mean, honestly, if this doesn't blow your mind, do you even have a soul? The Towers of Hanoi problem is a classic recursive problem that can cause endless amounts of frustration. When I first encountered this problem, it took me several days to come up with a solution, and quite honestly, I didn't feel like I understood the solution until after teaching it to many of my former students years later. The setup of the problem is as follows. You have 3 rods. One of the rods has some number of discs of varying sizes placed on
Let's
it,
first understand
with the largest disc
discs.
at the bottom and the smallest disc at the top. Your goal is to move these discs one at a time to a particular destination rod in the same configuration as the start. Before you get ahead of yourself and declare this problem trivial, there is one important catch. At any point in the process of moving discs, you are not allowed to move a larger disc on top of a smaller disc. This rule is what makes this problem significantly more challenging to solve. In this video, we will dive into the Towers of Hanoi problem in 3 distinct phases. First, we'll approach it from the perspective of a puzzle, where we'll try to come up with a strategy for various configurations. Then we'll transfer the strategy into a recursive program to solve this problem for any number of disks. In this section, I'll also show you some helpful tricks to solve challenging recursive problems like this one. And lastly, we'll deconstruct the recursion to understand what's really going on underneath the hood with some nifty animations that I'm pretty sure you won't want to miss. So make sure you stick to the end of the video. Alright, let's get started. Let's focus first on 3 disks, since the solutions to the 1 disk and 2 disk setups aren't too interesting for analysis purposes. I highly recommend pausing the video and taking a second on your own to see if you can find the set of moves to get these 3 disks to the rightmost rod. Our goal is to come up with a general strategy for solving this problem. If you're like me, your first go-to strategy in any type of puzzle is random guessing. And honestly, there's no shame in that. Random guessing is the oldest strategy in the books. So if I'm looking at this problem, the first thing I might try is to move the smallest disk to the middle rod. And then the next move is basically forced from there. I would move the green disk to the rightmost rod, since I can't move it to the second rod because that would violate the rules. After that, the next move that makes the most sense is to try and move the smallest disk to the rightmost rod. And at this point, after I've finished completely destroying the order of this problem with 3 random moves, I think it might be a good idea to evaluate what I've done so far. Well,
Yes,
unfortunately,
exactly.
It's not looking too good. It looks like we are a little bit stuck because what we really want is the bottom disk below the disks that we currently have on the 3rd rod. What we just did by random guessing seems to be pretty counterproductive to that point, so at this point in the problem I might decide, okay, I might just want to start over and reevaluate. But from this random guessing experience, we've learned one important fact. We need to first think about moving the largest disk from the first rod to the destination rod. And if we take this idea one step further, before we can even think about doing that, we're going to have to deal with the top 2 disks. And we have to deal with them in a careful manner so we can eventually move the largest disk to the destination rod. This means our only option is that we have to find some way to move the top 2 disks to the second rod. Okay, so now that we split our problem into more reasonable subtasks, let's solve them one by one. To move the top 2 disks to rod 2, we first move the smallest disk to rod 3, after which we move the middle disk to rod 2 and finish up the subtask by moving the smallest disk to rod 2. And now we are free to move the largest disk to rod 3. Alright, so what's next? Well, from here the solution is actually pretty clear. We need to move the top 2 disks from the second rod to the third rod now, and to achieve this, we move the smallest disk from the second rod to the first rod to get it out of the way. We then move the middle disk from the second rod to the third rod, followed by the final step of moving the smallest disk to the destination rod. And there you go, we've just solved Towers of Hanoi for 3 disks. Here's a quick recap of what we did. We first found a way to move the top 2 disks to the second rod, allowing us to then move this largest disk to the destination rod, and after this,
So the goal of this is to move the disks which are n-1 size of the biggest one. If the biggest one is size n, then you have to move all the disks size n-1 without disrupting the order into a different tower. So you move the disks to a different tower, all the disks except the biggest one into a different tower, without messing the order. So the order remains the same, as you can see. Then once all of them have been removed, you're able to remove the last biggest one because they're now out of the way. Now you could have moved these away out of the way as well, perhaps like this, but that would have been incorrect because, as you can see, no disks, no larger disk can be on top of these smaller disks. So you have to move these out of the way while preserving the order so that this guy can go to the correct disk. And that's it. That is the whole problem right there.
For this, we finished off by moving the top 2 disks from the middle rod to the destination rod. Okay, so now let's go one step further and see.
Now, if you keep repeating this, you will just solve the problem. That's it. It's just recursion from there. So you look at size n-1, take it to one rod, and then take the other ones to the final rod. However, it can be a bit more than that. Let's see
if we can solve this for the n=4 case by utilizing a similar strategy to what we just developed. Before I go through the steps to solve this, take a second to pause the video and see if you can come up with the steps on your own. Applying the general strategy to this new problem, we want to now move the top 3 disks from rod 1 to rod 2. How do we do this? Well, one interesting thing about solving this problem is that it's basically like ignoring the largest disk even exists and solving a general 3-disk Towers of Hanoi problem, where now our destination is the middle rod. Make sure you take a second to understand the mapping that we just did. And looking at the simpler problem, we know how to solve it now, right? We basically solved a version of it earlier. To solve this subproblem, we move the top 2 disks to the third rod. We achieve this by moving the top disk to the second rod, the middle disk to the third rod, and finish off by moving the top disk from the second rod to the third rod. This now makes way for the largest disk moving into the desired position. And now to finish off the subproblem, we once again move the top 2 disks, but this time from the third rod to the second rod. This subtask breaks down into moving the top disk to the first rod, followed by moving the second disk to the second rod, and ending with moving the top disk from rod 1 to rod 2. Notice the logic that we used here was essentially the same as what we did earlier, and this is something that will be immensely important going forward. In a sense, this is where the recursion of this problem really originates. Going back to the 4-disk problem, we now move the largest disk from the first rod to the destination rod. And now, following our earlier strategy, we now move the top 3 disks from the second rod to the destination rod. And the pattern once again shows up. This is essentially the same 3-disk problem we've solved many times now. We move the top 2 disks from the middle rod to the first rod, and to do this, we move the top disk from the second rod to the third rod. We then move the second disk from rod number 2 to rod number 1. And we finish the subtask by moving the top disk to the first rod. We then move the third disk from the second rod to the destination rod, and our final subtask is to move the top 2 disks from rod 1 to rod 3. Once again, we know how to do this. We move the first disk from rod 1 to rod 2, move the second disk to the destination rod, and finish off the whole problem by moving our top disk to the destination rod. And that's the sequence of steps for Towers of Hanoi with 4 disks. I know that was a lot, so let's do a quick overview of what we just did. We first moved the top 3 disks from rod 1 to rod 2. This required a couple of intermediate steps where we first moved the top 2 disks from rod 1 to rod 3. Next, we move the third disk to the middle rod, and then finish the subtask by moving the top 2 disks from the last rod to the middle rod. We then move the largest disk to the destination rod. And lastly, we finished by moving the top 3 disks from the middle rod to the destination rod, which had the same set of subtasks we've encountered several times. So now that we have a fairly good understanding of a strategy for this problem, let's now dive into a formal problem statement. We want to write a function Hanoi that takes 3 inputs, n, start, and end, and outputs a sequence of steps to move n disks from the start rod to the end rod. Here's a quick example of an input and output so that we understand how this problem statement works. If we pass in n equals 3, start is equal to 1, and n is equal to 3, what that means is our start rod is in rod number 1, and we have 3 disks on that start rod. Our end rod is rod number 3, and that's where our disks need to reach. For simplicity, let's assume that the start and end will always be between 1 and 3, and that they will never be equal to each other. Let's also assume that n will always be a positive integer, so we won't have to handle any weird edge cases. For this particular input, the sequence of steps that this function will output will look like the following. We've already gone over how these steps are generated from our strategy, but here's a quick overview of how the steps correspond to actual movements of disks. The basic interpretation is that A pointing to B means that we're going to move the top disk from rod A to rod B. Okay, so how do we get started on solving this problem? When I'm looking at any sort of challenging problem, I try to find the easiest thing I can do to help me solve the problem. Personally, I've noticed that there's definitely an intimidation factor in tough problems like this, and knocking out something easy can help you get over that initial intimidation. One of the easiest things we can do here is define a helper function that simply prints a move in the appropriate format. Defining this function is fairly straightforward to do and looks like the following. So now that we got that out of the way, let's shift our focus over to the main task. We need to find a way to programmatically generate a sequence of steps for n disks. We've already seen many clues in our investigation that point to the fact that we'll have to solve this problem recursively. But how in the world can we come up with something that works? This is by no means an easy problem, and before we get into that solution, I want to take a quick aside to go over an incredibly important concept when solving recursive problems. Whenever you are faced with a challenging recursive problem, there are 3 key steps that you should follow to make your life exponentially easier. These 3 tips have helped me throughout my years of learning computer science and saved me a lot of pain. The first step when solving a general recursive function f of n is to design a solution that works for f called on the input 1. This is often referred to as your base case. The second step is the one that's the hardest to accept, but what we are going to do is we're going to just go out on a limb and assume that f called on the input n-1 will work. The second step is often referred to as the recursive leap of faith. Once we've made this assumption, we will then show how we can define f called on n in a working manner using the function calls to f on n-1. Here's some intuition for why these 3 steps work. Think about solving this recursive problem f of n as trying to knock down n dominoes, where you only get to knock down the first domino. You want to show that the nth domino will eventually be knocked down. How do you do this? Well, you know that if you just have one domino, it's obviously going to work out because you can just knock it down. This is an analogy to step 1. From here, what you can do is just assume at some point the n-1th domino will eventually fall. This is the analogy to step 2. And now to guarantee the nth domino will fall, we have to put this domino just close enough to the n-1 domino so that when that domino falls, the nth domino will respectively fall. This is the analogy to step 3. And once we do that, all the dominoes fall. I want to emphasize here that all 3 steps are equally necessary for this to work out. If we don't get the base case right, that means the first domino never falls. If we don't make the assumption that f called on n-1 works, that's similar to the situation where the n-1 domino never actually falls, in which case there's no way that the nth domino is going to fall. And lastly, if we don't properly define the relationship between f of n and f of n-1, that's basically like putting the nth domino too far away from the n-1 domino, So in that case, the nth domino also never falls. It's by moving the domino close enough to the n-1 domino that the nth domino falls. So let's now apply these 3 steps to solving towers of Hanoi. Starting with step 1, we want to show how we appropriately handle the base case for this problem when n is equal to 1. That's easy enough, since if we only have one disk, all we have to do is move that one disk from the start to the end. In our problem statement, this is equivalent to calling print move with the arguments start and end. That takes care of step 1. Now let's move to step 2. In the process of solving towers of Hanoi for any n, what it means to assume that f of n-1 works is that we can just accept that any version of towers of Hanoi called on n-1 will work. It's important to remember that this includes a variety of starting and ending positions, and we're just going to assume that all of these subproblems work. Now, with that assumption that any call to towers of Hanoi on n-1 works, let's move to the third step, where we need to show how we can solve n-disk towers of Hanoi problems using the solutions to the towers of Hanoi called on n-1. There's one minor issue though. The first thing we need to take care of is we currently have a reference to the start and end rod, but we somehow need to have a reference to the other rod in the process. One quick and easy way to do this is by utilizing the rod numbers. Since the first, second, and third rods are labeled 1, 2, and 3 respectively, the other rod will always be 6 minus the sum of the start and end rods. And now that we have the other rod, we can now execute the first step of the strategy that we developed earlier. We want to first move the top n-1 disks from the start to the other. The neat thing about the framework that we have defined for solving this problem is that the first step is exactly equivalent to solving the following towers of Hanoi problem on n-1 disks. By the second step of recursive problem solving, we can assume this call works, so we can use it as part of our solution. This corresponds to the recursive call to Hanoi called on n-1 start and other. Once we've completed this step, we can then proceed to moving the last disk from the start to the end. This corresponds to a call to print move with the arguments start and end. And now, the final step is to move the top n-1 disks from the middle rod to the destination rod. This subproblem is essentially the same as solving Hanoi for n-1 disk, where the start disk is the middle and the end disk is the last disk. This means we can assume that the subproblem works as per our framework, and the corresponding recursive call is Hanoi with the arguments n-1, other, and end. And following these steps successfully solves towers of Hanoi for n disks, and this does indeed end up being a valid recursive solution. Now, before we move on, I want you to take a second and look at the final logic, and really take a moment to appreciate it. I mean, how crazy is it that such a seemingly tricky problem ends up having such a simple solution? I remember when I first solved this problem, my mind was absolutely blown away. I mean, honestly, if this doesn't blow your mind, do you even have a soul? This is really an amazing example of the power and beauty of recursive problem solving. And for completeness, here's a fully developed solution to this problem in Python. The nice thing about going through all this work is that the code basically writes itself. Now, at this point, some of you might be looking at the solution and think, okay, I understand how it works within the recursive leap of faith framework, but how does the actual recursion work? Fear not, let's answer that question. I think the best example to take a deep dive into is the one we started off with, Hanoi with 3 disks, where we want to move the 3 disks from the first rod to the third rod. The first recursive call will call Hanoi on 2 disks with the start rod as rod 1 and the end rod as rod 2. Here's what that represents. This recursive call forces us to go back into the function, where we now get another recursive call to Hanoi, this time on 1 disk, where we want the signal disk to move from 1 to 3. Here's a visual example of what this call is trying to achieve. And this recursive call will go back into the function where we actually hit our base case, which then prints the move from rod 1 to rod 3. And this is our very first move in the towers of Hanoi problem. Visually, what this represents is that all our recursive calls before have changed state because we now have officially made our first move. After making our first move, we have officially completed the recursive call to Hanoi on 1 disk, which now means we have to complete the recursive call to Hanoi on 2 disks. This means we now have to call print move on rods 1 to 2, which has the following effect. This is the second move in this particular towers of Hanoi problem. After completing the second move, we still have to finish computing the recursive call to Hanoi on 2 disks, which now makes its final recursive call on a single disk from rod 3 to rod 2, which has the following visual representation. This hits the base case once again, where we now make the third move, which is to move the disk from rod 3 to rod 2. Here's the effect of that on the overall problem. And this now completes our first original recursive call, which was step 1 in our earlier strategy of moving the top 2 disks from the first rod to the second rod. What's next is step 2 of that strategy, where we move the last rod from rod 1 to the destination rod. That's a simple print call, which has the following effect. That actually ends up being the 4th move in the sequence. This now leads us to the final step, which involves moving the top 2 disks from the second rod to the destination rod. That kicks off the following recursive call. This kicks off a similar sequence of events. The second recursive call goes back into the function, where we now make a recursive call with 1 disk moving from the second rod to the first rod. This hits the base case, where we now print this move, which is where the 5th move in the sequence comes from. Here's the effect of that on the overall problem. The 6th move then follows by now moving the disk from the middle rod to the destination rod. Here's the effect of that on the overall problem. And finally, the 7th and final step involves the final recursive call on 1 disk moving from the first rod to the third rod, which once again hits the base case that actually prints out the last move. And there you
Now-
have it. That's how the towers of Hanoi recursion unravels. It's really quite amazing how it all works out,
Unravels, yeah.
especially if it's your first time seeing it. So I highly encourage working through some
So you
examples
have
on
a
your own.
base case, right? In recursion, there are a few things you need to have. There's a function call and a base case. The problem will keep running until you reach the base case, and then it unravels from the base case back.
To convince yourself that things do indeed work.
And the base case here is that, the move, which you're doing.
Yeah, as they are supposed to. Before I conclude this video, here's a big picture recap of how we went about solving Towers of Hanoi. We first took a step back, didn't even think about the code, recursion, algorithms, or anything, and just tried to understand how we as someone trying to solve a puzzle might go about solving this problem. This is something I really encourage doing.
So visualization is quite important
When you encounter a tough problem. Don't be afraid to take a step back and take a look at things from a different perspective. Following this, we developed a strategy and used that strategy to implement our recursive solution. On the way here, we learned about the recursive leap of faith and how it can help us simplify particularly challenging problems. And lastly, we took a step deeper into the problem to understand how this recursion works out. Thanks for watching me, and as always, I'd appreciate it if you hit the like button if you enjoyed it. If you want to see more content.
Perfect. Now, shout out to reducible. You can check out the whole video again, but just to recap, it is basic recursion where you want to decompose the problem into, moving, let's say, n disks from some start to the end is the same as moving n minus 1 to another disk. The other disk is in 2 in this case, and then moving the largest one to the destination. And you keep doing that by moving the remaining disks to the other disk to then get the largest one to go to the correct disk. So we've reserved the destination as C. Now it's quite simple. You just have to think of it in terms of this. So there are 5 disks here. Forget 5 disks. Right now I want to, let's say if I want to move 5 disks, that means I have to move 4 disks to C. Okay. If I want to move 4 disks to C, sorry, I have to move 4 disks to B, so I can move the A here. But if I want to move 4 disks to B, I have to first move the 3 disks to C. If I want to move the 3 disks to C, I have to first move these 2 disks to B. If I want to move the 2 disks to B, I have to first move the first disk to C, and that's what happens. Okay, C. So it's recursion. Now, from C, what was the next step? You would move the next one to B. So first disks to C, fine. So before that we said we have to move the 2 disks to B. So once the first disk is out of the way, the second disk can go there, then the C will come back. Now the 2 disks are out of the way, so the third disk can go to the place. Now this is actually a problem of moving 2 disks to C, and that means I have to move, because now this is just moving 2 disks to C. That's just like moving, getting the 1 out of the way. So basically you get the n minus 1 out of the way, move n minus 1 to the other, and then move the n to the destination. And that's literally it. So let me write it down. Move n minus 1 to other, and move n to destination. 2 lines, and that's literally the whole of Tower of Hanoi. Okay, disk n. Disks n. And disks n is actually just moving, it's n minus 1 would then become, and this one is Hanoi n. So understand, moving Hanoi n from start to end, right? Move disks n minus 1 to this, and then move disk n to the destination. So start and well, let's say the n, which disk you want to move, the size of the disk, start and end. So the starting and the destination. Okay. And after that, it's quite simple, as you can see. So n, disk n minus 1, moving disk n minus 1 to other is quite simple, actually. This problem can actually be broken down as Hanoi, this is calling it back. But now this one, instead, you're not calling n, but n minus 1, and you're calling start. Start is the same. But now you're not calling start, the destination as the final destination, but the destination is other. And this will keep on going until you reach the base case, which is a single disk. And then you move that disk. That's about it. You keep moving until all the disks have moved to the destination. Now, if you have any doubts, you can rewatch the video and just message me. I will share the code with you. If you want to get the code, you can ask me for the code as well. That's all for today. Thank you. Have a great day. Have fun.